This is the second of two lessons on the Flight Management System, or FMS. The previous lesson covered components and hardware, whilst this one concentrates on equipment operation. There are about 30 or 40 pages available in the CDU display, depending on the model. Once the system has been initialized, these pages can be accessed either by the function and mode keys on the keypad, or by the line select keys available on the previous page. In this example, taken from one of the climb pages, the page allows you to select maximum rate of climb, maximum angle of climb, one engine out climb, or required time of arrival. However, the startup sequence always follows the same 4 pages, which are the identification page, the position initialization page, the route page, and the performance initialization page. You are not required to know how to use the CDU in this kind of detail for the exam, but we'll go through these pages to give you practical examples of how the pilot interacts with the FMC through the CDU. This is the ident page. The pilot should check that the aircraft model and engine rating in the FMC corresponds to the actual aircraft being flown. This may seem too basic to be necessary, but you should remember that all the Boeing FMCs have a strong family resemblance. It is possible for them to be put in the wrong aircraft or wrongly programmed, especially if the airline operates a mixed fleet. The same applies to the family of Airbus FMCs. Next, the start and finish periods of the nav database AIRAC cycle should be checked. In fact, if they are out of date, an alert message will be displayed. If the operational program and the latest software update are known, they can be checked too. On conclusion, the POS INIT line select key is pressed to move on to the next page. This is the position initialization page. The IRS has a non-volatile memory, and so will remember its last position before the previous shutdown. This is shown here. The airport, which is Amsterdam, or Echo Hotel Alpha Mike in this case, will also be remembered. The airport reference datum will be shown. If it is not already present, or needs to be changed, the pilot can overwrite it. The latitude and longitude is held in the nav database and does not need to be entered. Similarly, it is sufficient to enter the parking bay, gate Delta 16 in this example, for the latitude and longitude to appear. The pilot accepts or re-enters the initial position to commence IRS alignment. It is possible to select different time zones on many systems, but usually unnecessary. All flying operations are conducted in Coordinated Universal Time, which, for all practical purposes, is the same as GMT. Local times are not generally used in aviation. On conclusion, the route line select key is pressed to move on to the next page. The route page starts with the departure and destination airports. In this example, they are Amsterdam Schiphol and Liverpool John Lennon Airport. It is usually sufficient to simply enter the company route number. In this example, flight number 602 is the company's route from Amsterdam to Liverpool. And it is a repetitive flight plan. The pilots should know which runway is in use by the time they program the FMC. If the company route is not already programmed, the route can be entered using the VIA and TO columns. This page offers us only one option: performance initialization. Here is the Performance Initialization page. The gross weight in metric tons in this example is taken from the dispatcher's trim sheet. The desired cruise altitudes are entered. The planned fuel from the trim sheet is entered. This is compared with the actual fuel gauge measurement, which is directly connected to the FMS. If there is a discrepancy larger than a specified limit, a warning will be given. The zero fuel weight is entered. This is added to the fuel figure. The answer should be the gross weight. If it is not, again, a warning is given. The forecast wind, ISA deviation and static air temperature are entered to allow the FMS to plan an estimated flight time and fuel burn. In flight, as actual data is gathered, these estimates will be continuously modified. The cost index is entered. This figure modifies the target cruising speed in order to balance the fuel costs and maintenance costs of the flight in the most economical way. This will be explained shortly. As before, there is only one page we can go to. The N1 limit can be set to reduce engine wear in the climb. Let's explain cost index. We'll use a worked example. Suppose we have an aircraft that can be flown at either high-speed cruise or long-range cruise. Let's say that over a particular route, high-speed cruise takes 3 hours and long-range cruise takes 3 hours and 10 minutes, but uses less fuel. Your job as an airline pilot is to operate the aircraft for your company as economically as possible. Which do you choose? You might think that the answer is obvious. You would select long-range cruise. But it's not as simple as that. There are other operating costs. Let's now suppose that the aircraft has to go in for planned maintenance every 1,000 hours, and it is then out of service for a week. In that time, not only is the airline paying for maintenance, but the aircraft is out of action, not generating revenue. These figures, by the way, are simply illustrations. They are not necessarily based on any particular aircraft. Let's say that if we fly at high-speed cruise, we can make 300 revenue-earning flights between maintenance. We'll allow 100 hours for positioning flights and crew training. However, if we fly to save fuel, each flight is longer and we can only get 284 revenue-earning flights in the same maintenance interval. This is a difference of 16 flights, each of which might have 100 passengers on board. We have lost up to 1,600 fares between maintenance intervals in order to save some fuel. Is it worth it? The answer is that it depends on the relative cost of fuel and cost of maintenance over the route that the aircraft is operating, and these will be different in different parts of the world. However, for each route, they can be calculated by the operator's cost accountants. There will be an optimum point which, for any particular route, is the most economical speed to fly. Cost index attempts to quantify this. It is determined by dividing aircraft operating costs by fuel costs. Only those portions of operating costs affected by trip time are included in the calculation. The range of values is then put on a sliding scale, which is from 0 to 200 for the Boeing Classic series of FMCs. If 0 is selected, the FMC gives maximum range airspeed and minimum trip fuel with a low-speed descent. If 200 is selected, the FMC gives VMO or MMO for climb and cruise and a high-speed descent. The company will specify a cost index to be used for each route. A required time of arrival mode is available in order to arrive on time at some designated waypoint, such as the final approach fix, holding fix, or airport. The FMC computes a recommended takeoff time, then gives target speeds to fly, and continuously adjust them in flight. Speeds are automatically corrected for in-flight winds and route changes by adjusting the cost index. If RTA mode is used, taking off late will add to the cost, as the aircraft will have to fly faster. There are occasions when the crew may be required to navigate to a waypoint that is not already stored in the permanent navigation database, for instance, following an air traffic control instruction. In this case, it is possible to create a new waypoint. This can be in one of 4 formats. The first is the simplest, latitude and longitude. Next is called place bearing and distance. For instance, Sierra Alpha Mike 180/45 means 45 nautical miles range on the 180 magnetic radial from Southampton VOR. There is also place bearing/place bearing. Sierra Alpha Mike 122/Delta Victor Romeo 218 is where the 122 Southampton radial crosses the 218 Dover radial. Note, however, that there is no place distance/place distance facility, as this would result in 2 possible solutions, and the FMC would not know which one to take. Finally, there are along track waypoints. If the route, for example, is a direct track between Southampton and Dover, then Sierra Alpha Mike 030 means 30 nautical miles along the route after Southampton, and Delta Victor Romeo -030 means 30 nautical miles before Dover. But there is no across-track facility as, again, this is not unique. It could be anywhere along the displaced track, and so is not allowable. These created waypoints are normally put into the temporary nav database and are therefore automatically erased at the end of the flight. As we said earlier, the IRS initial position is inserted using the position initialization page at startup. From this point on, there are no further updates directly to the IRS. However, the FMC position is updated. The first of these updates comes at the start of the takeoff roll. The FMC navigation database contains the position of all runways thresholds in the company's route structure. As the takeoff roll is commenced, the throttles are advanced. A contact on the throttle quadrant is called the takeoff go-around switch, or TOGA switch for short. Operation of the switch automatically updates the FMC position to the takeoff threshold. It is also possible to input a displaced threshold. Suppose that we do not need to use the whole runway length and have decided to take off from 2,300 feet past the threshold. In this case, the pilot inputs a correction factor for the displacement distance, and the new position is automatically calculated by the computer as part of the update. We are now going to look at some typical alert and advisory messages. On most systems, there are around 40 to 50 messages, and they vary in detail from system to system, so you are not required to learn these by heart. This is just to show you some representative ones and to show you how the pilots and the FMC interact. You'll remember that alert messages have the highest priority, and they identify a condition which must be acknowledged and corrected by the crew before further FMC guided flight is advisable, or even possible in some cases. Advisory messages have lower priority and inform the crew of CDU entry errors or system status. Here is a typical alert message. Thrust required. It means that VNAV is engaged. We are past the computed top of descent, and additional thrust is required to maintain the required descent path and speed. Here is another. Runway not applicable for SID. It means that the runway which the pilot has selected is not compatible with the required standard instrument departure. Details of runways and SIDs are stored in the navigation database, and it can pick up these types of mismatch. Similarly, we have the alert message, Runway ILS Frequency Error. The FMS knows which instrument landing system frequency is associated with each runway. If the wrong one is selected, it will pick it up. Another possible message is Unable Cruise Altitude. This is because the journey is too short for the requested cruise altitude. Suppose the route distance is 210 nautical miles and we select flight level 350. The computer will calculate the distance required for the climb to that level, taking into account weight, ISA deviation and wind. A typical figure would be 105 nautical miles. It also calculates the descent distance, taking into account the same factors. Typically, this might be 110 miles. However, the computer works on a minimum acceptable cruise time of 1 minute, which is usually about 7 miles. This would give us a minimum trip distance of 222 miles. We would therefore get an Unable Cruise Altitude message. If we then select a lower altitude, it should work. By contrast, we have the advisory message, Max Altitude, Flight Level 390. This is because the aircraft is simply too heavy. We have asked for a cruise altitude greater than the maximum attainable at this weight. Let's now look at a serious alert message, Insufficient Fuel. We'll put ourselves into a typical situation first, then we'll work out how the FMS has arrived at this conclusion. Finally, we'll work out what we can do about it. Here is a route. We'll say that we don't normally take a more direct path because we have to follow the airways. There is an en route alternate. An alternate near the destination where the weather is bad. And an alternate further away where the weather is within limits when we take off. This is the one we have to nominate. You are here when you get the insufficient fuel message. Firstly, let's work out how the FMS has arrived at this conclusion. It knows where you are, and it is continuously working out the length of the rest of the route. It knows your ground speed, so it can work out the remaining flight time. It knows the present fuel and the fuel consumption rate, so it can work out how much you will have on arrival at the destination. It then compares this estimated fuel on arrival with the minimum reserves. Your first reaction might be to make an immediate en route diversion in order to stay within your fuel reserve minima. However, there may be other courses of action, and the FMS can help us perform these calculations and see whether the figures make these options viable. Firstly, you could ask air traffic control for a more direct routing. They might not be able to give it, but it's worth a try. If they say yes, the FMS can work out the new fuel used and revised fuel on arrival. This may solve your problem. You could also think about choosing a different flight level. Climbing 4,000 feet will probably give you a higher TAS and a better specific air range. If you have a strong headwind, perhaps going 4,000 feet lower might reduce it. In both cases, the FMS can work out the revised fuel and time for you. Also, it may be that since you took off, possibly several hours ago, the weather has changed en route. Maybe the nearer diversion is now within limits. If any of these solutions, or a combination of the three, works, then you can proceed safely and legally to your destination. The FMS is a very capable computer, but you don't follow its instructions blindly. It has various what-if options, which should be used sensibly. It does not replace the need for airmanship and captaincy. Let's summarize this lesson. The first 4 pages in the startup sequence are always the same: identification, position initialization, route and performance initialization. The route is usually entered simply using the operator's flight number. Cost index is determined by dividing aircraft operating costs by fuel costs. The range of values is then put on a sliding scale, which is from 0 to 200 for the Boeing Classic series of FMCs. 0 gives minimum trip fuel and 200 gives minimum flight time. A required time of arrival mode is available in order to arrive on time at some designated waypoint, such as the final approach fix, holding fix, or airport. New waypoints can be created by the pilots using one of the 4 acceptable entry methods. These cannot be entered into the permanent memory. The IRS position is not updated after initial entry. However, the FMS position is first updated on takeoff. Finally, we looked at some typical alert and advisory messages. This concludes the 2 lessons on the FMS.